Welcome to Chapter 17. In this video, we're going to derive the formulas for Sphubical coordinates. This is somewhat of a continuation of Chapter 7, which was on squircular coordinates, so we'll start with a little recap. First, I'd like to recall the important equations derived in Chapter 7. The conversion from squircular polar to Cartesian, and vice versa, the conversion from squircular to circular polar, and a way to represent height as a ratio of norms. To be consistent when it came to the concept of radius on the squircle, we had to create this new parameter r base p, for which, when it's constant, all the points will lie on the squircle with a radius of that value. Another important thing to note is that these thetas are the same as the circular theta. Angle is measured in the exact same conventional way we're all used to. So we'll be doing the same thing with our 3D spherical coordinates. We'll want to preserve the angles theta and phi from spherical coordinates, but introduce a new coordinate, rho base p, which will tell us which sized spube we're on. Now we'll derive our conversion formulas. We're going to start with that we naturally want rho base p and only rho base p to be the p norm of our rectangular coordinates x, y, and z. We'll substitute the spherical coordinates in and factor out rho. We want both rho and rho base p to be non-negative, so we can get rid of their absolute values here. Now, we want to solve for rho, just like in this equation from Chapter 7. You might be able to see where I'm going with this, so I'll go ahead and denote this large expression as the third-dimensional height function, where of course the 3 denotes that this function is valid for a maximum of 3 dimensions. If we compare this definition with the 2D height, we can start to see the similarities. Within the negative pth root, we're given the sum of rectangular coordinates over the 2 distance from the origin raised to the pth power, which then can be written as the 2 norm of the rectangular coordinates over the p norm of the same. Now, we're finally ready to get our equations for spherical coordinates. We'll take the spherical coordinate equations and the spherical Sphubical conversion to replace rho with rho base p, and voila! There it is! Interestingly, there's another parameterization that satisfies the equation of a spube and uses our 2D trig functions instead, but unfortunately, angle is not preserved here. If we take the position where rho base p is 1, theta is pi over 4, and phi is pi over 4, and apply the formula for phi, we don't get that phi is pi over 4, unless p equals 2, of course. So these coordinates don't work the way we want them to. Then these must be our Sphubical coordinates. But while we're here, why don't we go an arbitrary and finite amount of steps further? What about n-dimensional Sphubical coordinates? What we'll want to do is take this position vector described with n rectangular coordinates and describe it as a p distance from the origin and a collection of n-1 conventional angles. We'll start this out the same way we did for 3D Sphubical coordinates. We'll define r base p as the p norm of all the rectangular coordinates, and we want to do the same thing of replacing them in this equation with their spherical counterparts. And since overleaf won't let me typeset this substitution in one line, I'll use these products as a shorthand and put it under a summation. Hopefully it's clear what I'm doing here with the notation, because I honestly think it's swanky. But anyway, we want to do the same thing as before and solve for r. Then call that large term n-dimensional height, where capital phi is a vector of n-1 angles. Here we can again see that our height can be represented as the 2 norm of rectangular position over its p norm. And now we'll define our coordinates by substituting for r using the spherical Sphubical conversion, and that's it, I guess. Kind of anticlimactic, but there you have it. Our higher dimensional height functions, conversion equations for spherical, representation of height as a ratio, and conversion for rectangular. Next time we'll be doing Jacobians or volume elements for n Sphubical coordinates, so stay tuned. Bye!